Okay, today we're going to be looking at the second planet from the Sun, and that is Venus. Now, Venus is a really interesting planet. If you want to get all the details on Venus, like the statistics, if you look in the accompanying textbook, the Introduction to Astronomy textbook, there'll be a little table at the beginning of the Venus chapter with all the information about Venus. So when astronomers first looked at Venus, they thought of Venus as like the twin of Earth, our sister planet. And so we're going to look at this idea of Venus being our sister, our twin planet, or is Venus more like an evil twin and not really like Earth at all? Now, the things that made Venus, astronomers think of Venus as our twin was, firstly, Venus and Earth are very similar in size. Venus is just a little bit smaller than the Earth. Early astronomers, when they looked at Venus in telescopes, they saw this really beautiful looking planet. It looks all these wispy clouds. It looks really quite pretty. And even before telescope astronomy, Venus is this really beautiful, bright star in the night sky. And you compare it to Mars. Mars is this red sky. So they would look at this beautiful white star of the planet Venus, and they'd look at the red one. So Venus was named the goddess of love. It was thought to be really beautiful, and Mars was the god of war. It was red and looked angry. And so this kind of idea that of Venus kind of grew up around it. Looked lovely. It's about the same size as Earth. However, astronomy has developed, and now we know that Venus is more like a place that would be more in keeping with a biblical vision of hell than of a beautiful paradise like Earth. So there's some strange characteristics to Venus. First, it rotates very, very slowly. Now, the concept of the rotation of a planet, we call this the sidereal rotation. So this is how long it takes to go round its axis. So the sidereal rotational period of Venus, so the Venus day, is 243, just over, Earth days. And that is longer than a Venus year. So it takes 224.7 days for Venus to make a rotation around the Sun. So that's how long the Venus year is. A bit shorter than the Earth year, which makes sense because its orbit is going to be smaller because it's closer to the Sun. But the year is shorter than the Venus day, which is really kind of weird. The rotation of Venus is also in the opposite direction. So we call this, if something's in the opposite direction, we call this retrograde motion, if it's going in the opposite direction. Now I've got this really nice little image here which shows you the different sidereal rotations of the planets kind of side by side. Now we saw with Mercury, Mercury's got a very slow sidereal rotation as well. But not as slow as Venus. Venus looks like it's not even moving. It looks kind of just standing still. The Earth, here's our Earth day, is 23 hours and 56 minutes long. So actually, a day is not actually 24 hours long. It's just under. And Mars has got kind of similar to Earth in its rotation, its day. Jupiter is super fast. Jupiter has the quickest rotational sidereal rotation of all the planets, and you can see that with all these giants, the gas giants and the ice giants, they actually spin really, really quite quickly. So Venus is significantly slower than all the other planets, which is we have to ask, why is it slower? And what is the deal with this retrograde motion? Because these are really quite unique to Venus. So let's think about the slow rotation first. So how do we know the rotational period? How can we measure this? So what astronomers do is we send spacecraft and they orbit the planet. So here we've got a picture of, this is the Magellan spacecraft, which visited Venus in the 1990s. And so this spacecraft orbits the planet and it's got very precise radar technology on place. So the radar would, let me just get my annotation up. So if you imagine, here's the surface of the planet. Here's our space probe, and it's got a radar, and the radar beams a signal down to the surface. So say we've got let's say we've got a volcano here. So it sees this volcano, and then that'll bounce back, and we change the color, so it's a bit different. So they'll bounce off the volcano, and that then comes back up and gets picked up. So that's how kind of a sonar is produced. So this is doing this all the time, and the spacecraft is orbiting round, but the surface of the planet is also spinning because it's spinning on its axis. So we know how fast this craft is orbiting, but we don't know how fast this planet is orbiting. And by measuring the differences in the signal being received back by the spacecraft, we're able to calculate the velocity, the speed of the planet as it orbits round its axis. So this is how we are able to know the different rotations of the different planets. And so this would be mapped. The Magellan spacecraft not only worked out the sidereal motion rotational period of Venus, Magellan also through radar technology was able to map the surface of Venus as well by doing this whole radar process in the same way that sonar is used to map out the ocean floor. It's exactly the same type of technology. Excuse me. Okay, so we did this with the Magellan spacecraft in the 1990s. 16 years later, the European Space Agency sent another spacecraft to Venus, and they got a different result. They worked out the sidereal motion was 6.5 minutes longer. So this showed that Venus appears to be slowing down. Now, there's some reasons that we believe this to be the case. The most plausible is that the atmosphere of Venus, it's got a very dense atmosphere, which we're about to find out about. And this atmosphere is moving really, really quickly. So that like in the upper atmosphere, there's like hurricanes raging. They're really fast. There's really dense clouds. And this creates surface friction with the planet and is actually slowing the planet down. So not only have we got this really slow day, this day is getting longer because of this reduction in the orbital period. The slow rotation also means that the planet cannot generate a magnetic field, which we'll talk about more in a little bit as well, but that's quite an interesting result from that. So let's look at the retrograde motion. So to talk about the retrograde motion and its consequence, we need to think more about the theories of solar system formation. So first, when we think about the word theory, it means it's an idea that has not been proven. It's not a law, it's still a theory, it's an idea. So we see in space things called nebula. So a nebula is a region where there's lots of gas and dust, and we can see this through telescopes. And it's believed that in the nebula, the gas and dust will start to clump together, it'll be drawn together under gravity. And in these regions, this is where stars are made. So you'll get this thing called a protostar. So a protostar is, oops, a daisy. I'll get the annotation up. A protostar is a star, it's like a baby star basically. And so we've got this protostar that is formed in the nebula, but we've still got this gas and dust, and it starts to rotate really fast round and round and round this protostar. And as this gets bigger, more stuff gets pulled in, and it's all about gravity. This is all working under gravity. But within this swirling mass of cloud and dust, bits of dust and cloud and gas will kind of clump together, more dust will clump together. So you'll get these rocky bodies forming, which become planets. However, we see Venus, so all this is going round and round in this motion. You're not going to have some big clump going in that way. It's not going to happen. So they're all rotating in the same direction. Therefore, it would make sense that when they clump together to form planets, the planets all go in the same direction. But we're seeing Venus in the, so we'll draw Venus here, is going against the flow. It doesn't make sense, and it is a problem that scientists don't have an answer for. It completely goes against our current models for solar system formation. And we'll often see this, that we'll have models for different things we see in the universe, but not just on our solar system, but on a galaxy and wider scale. And there'll be these little, we'll find these pieces of evidence of these enigmas that completely don't fit into the puzzle. So the rotation of Venus is a big problem for the models of planetary formation that we have. And there's a few theories of what may have caused it to be an opposite retrograde motion, but there's nothing quite nice enough and succinct enough to really explain it in full. Okay, so let's talk about the atmosphere of Venus. So the atmosphere of Venus is really thick, and so when we look at Venus, let me just go back a few slides to this one. This is what we see when we look through a telescope, just a normal telescope of Venus. We see this lovely kind of wispy cloud. You can't see any features because the atmosphere is so thick, our telescopes cannot penetrate to the surface of Venus. The light is just not going to get through. The atmosphere is so dense that if you were to stand on the surface of Venus, hypothetically, it would crush you because it's 90 times more. The atmospheric pressure is 90 times more than that on Earth. Let's quickly just define what we mean by atmospheric pressure. So if you think about, there's particles all around us in the air that we're breathing right now. All these particles are constantly in motion, and so say we have some piece of ground, and so these particles, some will bounce off like that. They're bouncing off things. So pressure is the force exerted by all these particles over a certain area. So we define it as the force in newtons per meter squared. So if you think of this as a meter square, and the force in newtons that has been exerted on this meter by all these gas particles bouncing off it, is what we define as being the pressure. So our atmospheric pressure is just perfect for us to be living in, but on Venus it's 90 times stronger. It's made up mostly of carbon dioxide, but there's also quite a lot of sulfur-based compounds in there as well, like nitrous oxide and sulfuric acid, sulfur dioxide. There's some nitric gases as well, but it's mostly carbon dioxide and sulfur-based compounds as well. That makes the planet pretty stinky. It would smell like a rotten egg. And this is because it's believed that the gases are believed to come from volcanic activity. Venus is still volcanic, and it has been very, very volcanic in its past, and it's this volcanism which has led to this really dense atmosphere. And if you were to go to places today on Earth where there's a lot of volcanism, you would discover they can be really stinky places because of the sulfur in the compound. So it's a nice yellow colour to go with the sulfur, because sulfur smells like rotten eggs. So it's a pretty nasty place to go to. The density of the atmosphere results in Venus being the hottest of the planets. So it's hotter even than Mercury, even though Mercury is right beside the sun. And this is because these gases have created what's called a super greenhouse effect, or a runaway greenhouse effect. I'm going to talk about that a bit more in a little bit more detail on the next slide. Another result of the clouds is they reflect sunlight. So we looked at that the first slide with that nice wispy picture of Venus. They look kind of whitish, slightly yellow tinge, quite pretty. Those gases are highly reflective, so the sun just bounces off the top of them, making Venus when Venus is at the best position for us to see. It's the brightest object in the night sky after the moon when it's in its optimum position. So it's really quite beautiful. Venus is what we call, if you hear the term, the morning and evening star. So that you often, when Venus is visible to us, it'll appear in the morning, and at night is a very, very bright white star, and it'll be the brightest star in the sky, and that's Venus. It's a very pretty thing to look at. Okay, let's talk more about this runaway greenhouse effect. So let's think about the Earth to begin with. So the Earth, we hear about the greenhouse effect as a negative thing linked to climate change, but there's an element where we need a degree of this kind of greenhouse effect thing happening on Earth, and I'll explain why. So the sun sends its radiation to the surface of the Earth. Some of that radiation is actually absorbed by our atmosphere, so the UV light is mostly absorbed by our atmosphere, which is good. It protects us. The sun gets to the surface, warms our planet, makes it a nice place for us to live. Some is then bouncing back off and is lost into space. But some is trapped. So we've got our atmosphere, the upper atmosphere, which is made up of these, what they're called greenhouse gases. So the greenhouse gases are defined as gases like carbon dioxide, methane, CH4 is methane, nitrogen oxide, and water, and O3 is ozone. So it's a molecule of oxygen with 3 oxygen atoms. The oxygen we breathe is O2. So we can't breathe O3 ozone, but we breathe O2. So these gases are make up the majority of our atmosphere, and it's like a blanket. Some of the radiation is allowed to penetrate out, but we've got enough of these greenhouse gases to provide a blanket, so some of the heat doesn't escape and come down. So the problem is we need a balance. Too much greenhouse gases, then is too much radiation trapped. Too few greenhouse gases, and too much of the radiation escapes. So in Mercury, there's no atmosphere. So during the day, the full heat of the sun hits Mercury, and it becomes very, very, very hot, which is logical given its location. But the Mercury night, there's no atmosphere, so all the heat just escapes back out into space. So there's no greenhouse effect on Mercury at all. So on Mercury, you got this huge temperature variation between the day and the night. Venus is the opposite. Venus, think about how slow the Venus day is. The Venus night is going to be very, very long, but the temperature between daytime and nighttime is pretty much constant. It's like inside of a pizza oven all the time, because all the heat from the sun gets trapped and is not radiating back out. And you've got this heat from the volcanic activity, from all this volcanic activity that is just built up and built up, making Venus this insufferably hot place. As I said, it is as hot as a pizza oven on the surface of Venus all the time. So our greenhouse effect is that kind of, again, it's that Goldilocks zone of we've got it kind of just right. We need some of those greenhouse gases to trap heat in so we don't have these huge temperature fluctuations between night and day. But again, we need to release some of that heat. Otherwise, you don't want your planet having a runaway greenhouse effect like Venus, because Venus cannot support any water at all. It just burns off. So although the atmosphere on Venus is made up of, there's some water, there's a little bit of water, there's like there's not water droplets, there's sulfuric acid droplets within the atmosphere of Venus. They don't have sulfuric acid rain on Venus because it just evaporates on the surface. The rain does not fall on the surface. It's just dry, arid, hot, and pretty nasty. So I mentioned the Magellan spacecraft. That was the first spacecraft to make a radar scan of the surface. And this is a false color image that takes that data from radar images to create this picture of what the surface is like. So we've got areas with mountains, we've got lowland areas. These are not rivers. These are probably being caused by flows of lava. So we see on Venus, we've got these mountains, we've got volcanoes. This is these are computer generated images, again from radar images, that will have a look to kind of create the topography of the landscape. We see volcanic activity, we see mountains, some quite big mountain ranges. The biggest mountain on Venus is actually bigger than Everest. But what we don't see is many craters. And the craters that we do see are big. We don't see any small craters on Venus. And this is most likely because any smaller meteorites that were coming towards Venus and would have hit Venus are burnt up in that atmosphere before they even get a chance to hit the surface. So to be able to penetrate the surface and cause damage, they have to be pretty big to get through the atmosphere. The other reason there's going to be few craters is because of the volcanism. The surface of Venus is what we'd call geologically new. It's not had a long time to weather and just sit there and gather all this craters like Mercury or like the moon. It's been covered, a lot of it's been covered up again by volcanic activity. Kind of like what we see on Earth. We don't see the Earth being heavily cratered, and that's because of sometimes it'll be covered up by geological activity like plate tectonics or volcanism. And we also have weathering on Earth, which would cover up volcanic meteorite crater activity. So Venus doesn't have the weathering, but it does have this volcanism. We have landed space probes on the surface of Venus. So in the 1980s, the Soviets, so USSR back then, they sent a probe, they sent a series of probes called the Venera missions. So there's a few of them, and they managed to land on the surface of Venus. Some of them didn't survive the atmosphere. It took them a few attempts. They just got burnt up. But some did, and they lasted maybe just a few minutes, a very short time before they succumbed to the heat and the pressure, and the space probes were basically dead. But those that survived did send back these very grainy images of the actual surface of Venus before they were destroyed in this hostile environment. these are some of the, again, these are images that we've taken from the radar images and computer generated, so you can see these kind of, this is all caused by volcanism. And so you can see these kind of volcanic craters. So you've got these kind of shield volcanoes on the surface of Venus. And we also have these kind of wrinkly, cracky features. They're called tessera. They're the only seen on Venus. I'm not 100% sure of the source of them. They cover about 7% of the surface. The most likely explanation is that the crust of Venus is really thin. And if you think about if you've ever made jam and you're boiling hot jam, it's very viscous, and then you take some out to cool it, there'll be a thin, on the layer of the jam, there'll be a thin bit will start to more solidify a bit more and go more kind of jelly shape and go less liquidy. And if you were to move it, you'd have like a crinkly, you can push your finger along and it will crinkly. And that's a bit like what we're seeing here. So we've got the volcanism. Because I just mentioned we've got this thin crust, we don't have plate tectonics, because plate tectonics is a result of cooling. So on the Earth, you've got the mantle and you've got a thicker crust, which has where there's been cooling and the rock has solidified, and then the tectonics are then moving on top of the mantle. We don't see that on Venus. The crust is thin due to the intense heat by strong convection currents inside the mantle that's constantly moving, churning everything up, which is what we think are the result of that crinkling effect that we just mentioned. Geologically, the composition is very like Earth. There's basalic rocks in the crust, but there's no granite like on Earth, so it's a bit different, which is, again, this is all kind of characteristic of intense volcanism. We mentioned the tessera. Inside the actual center of Venus, we've got an iron core, and it's molten, but there's no magnetic field. That's because there's no strong convection currents within the core, like we have on the Earth's outer core. And that, as we've mentioned, is due to the slow rotation of the planet. So here's a little image of Venus's interior. So we've got this thin core, we've got this mantle, and of course we've got this in here, we have our strong convection currents because of the intense heat. But the iron core, we'll change the color because that will not show up. Yellow and yellow does not show up. The iron core, no magnetic field. And we have the thin crust here. Let's clear these and get rid of that. So this is an interesting little feature. If you were to observe Venus through strong binoculars but a small telescope, you would notice that Venus actually has phases like the moon. And when astronomers first saw this, this was really strong evidence for the heliocentric model of the solar system. So the heliocentric is what we have: the Earth at the Sun at the center, and the planets orbiting. And because when you can see the phases of Venus, like this is Venus as a crescent. It shows us that we are not at the center. If we were at the center, Venus would not have phases. It would always just be a disk. But the phases of Venus reveals that as evidence for that heliocentric model, and it was a bit of a game changer when it was first observed through telescopes. So I hope that was helpful and interesting.